Okay, so good morning. I hope you had time to rest a little bit over the weekend. So let me just see how the blackboard looks like here. 1, 2, and 3. Okay, let's start with this. Okay, so in this week we are going to talk about discrete optimization. Discrete optimization. And let me just start by saying that what I'm going to talk, so today I'll tell you where Matthias, what's the difference between what I'm going to talk about and what Matthias is going to talk about. But the material that I'm going to cover here draws, there are parts of some recent book which I just completed. So this is really going to be out. It's in print, so it should be really out in a few weeks. And it's entitled Nonlinear Discrete Optimization. An algorithmic theory. Okay, and it's created by me, if you have not seen my name so far. And it's going to appear in the Zurich lectures. In Advanced Mathematics, which is published by the European Mathematical Society. Okay, so this is it's a 150 pages book. It's going to appear in a few weeks. And for reference for the talks here, there's a link from the website, you probably have seen it, to an older version, a preliminary partial version of this, which I taught in Zurich at the last year. So so you can use the references for the talks. Okay, so what is discrete optimization? So what is discrete optimization? Well, the general problem is very simple to state. You want to minimize, it's an optimization problem, minimize or maximize some objective function over a set of points. That's a general optimization problem. And what makes it discrete is that the set is a set of integer points. So Z stands for the integer. These are integer vectors of dimension D. And this, of course, naturally sits in Rn. So we are going to use convexity quite often later. So when I talk about convex functions, I mean in Rn. And actually, right away, let me say that I'm going to assume throughout that the set is finite. So if it is not finite and we are doing nonlinear optimization, then this is quite hopeless. And also in applications, it is typically the case that S is finite. So S is going to be a finite set. And there are issues of how to actually detect if it is finite or not. But in this short series, we are not going to discuss this. So S is finite. And F is a function from Rn, let's say Zn to R. So I need it to be defined only on integer points, but usually it will actually be a function on the entire space Rn. Okay. So this is a simple problem, looks like a simple problem, but so what should we, if this is a finite set, it looks like a trivial problem. You just check every point and pick the best, right? But what we are interested in is algorithms, efficient algorithms, to do it in an efficient way, and usually we mean, by efficient I mean polynomial time, so we want polynomial time algorithms, mostly. And last week, there's also hard problems, and usually there was no okay, let me not say, but I should say that discrete optimization problems are typically very hard, even if the function is linear. but we want to solve it in polynomial time. And you don't really need to know much about complexity. There's going to be a certain size of the problem, but roughly think about n, for example. So polynomials mean something like n to the 10 is good. It's not so good. I mean, n squared is better. Running time, I mean, time. So n squared is better maybe, but in my monograph and in this series of talks and also in Matthias's lectures, we don't really care about the exponent so much. So now that it's polynomial, and so asymptotically, when n goes to infinity, we can solve large problems. And something like 2 to the n or n factorial, that's not good. That's exponential. And of course, n is not going to be the only part of the input, but let's just start with this. Okay, so to make the problem precise, we have to tell you how is the input presented. That's the main issue here. So let me start with the function. I mean, to talk about algorithms, we need to tell you how the function is, input is presented. So the function, the presentation of the data. So the function, first of all, there may be several types of functions, and this is, of course, going to affect the algorithms. We are going to exploit the structure of the function. So first of all, linear, that's the most standard function. And then we can identify this with some vector. And we may take the vector to be integer also. So this is the standard inner product. I'm going to write it simply like this, without the transpose usually. Okay, this means the inner product. We are working in the exact arithmetic or Turing computation model. So we have to use rational numbers, actually, when we have to do operations. And so if this is rational, we can scale it up and assume that this is integer. Okay, so this is an integer vector. So linear means an integer vector. There are multilinear, or let's call it multi-criteria. It is not quite multi-criteria. So I can actually extend this and look on things like this. Well, now W is a D by N matrix. F is a function on RD, let's say ZD. So that's another type of function which is useful. It is, of course, more general than linear. And so you see how this function looks like. The idea is the following. Look on the matrix and you think about the rows. So you have several rows. Each row represents one linear function, like this one. And now I have few rows. That's D rows. And they can represent criteria, D criteria. Or if you have a game with players, this can be interpreted as utility of D players. So we take a vector, a possible solution, multiply this, we get a D-dimensional vector, but we want to do optimization, so eventually we must have a real number, and then we apply some balancing function. That's the interpretation of such functions, but mathematically there's simply these composite functions. And for such function, we can actually exploit the fact that we first go to a smaller dimensional space, D. And again, note that this includes linear functions. It's a very special case, and linear functions are also very hard, NP hard in general. Another type of function, we may look on some quadratics. I'm not going to discuss this much. Quadratics, polynomials, like you see in last week, polynomial functions, polynomial, separable. We're going to talk about separable functions, which means that the function is a sum of univariate functions. Again, this is more general than linear. Linear functions are separable. So there are also lots of functions. Norm, let me also mention something important. Norm, the pth norm. And again, to get integer, it doesn't matter if you take the pth power, so we're going to use the pth power. So this is the sum of this. And the L infinity norm also. So these are functions that we will consider and see what we can do about them. So this is the type of function we are going to exploit. And also, quite often, we are going to use functions which we just know that they have some properties of convex or concave functions. These are very important also in continuous optimization, as you've seen last time, convex and concave. And now another issue is how is the function presented to the algorithm, so I can actually talk about complexity. What is the size of the input? So what is the size of the input for such function, for linear function? What's the presentation? How do the algorithm get the function? How does the algorithm get the function? W, you simply get the list of entries. That's very easy, right? Integer numbers, you write them, and then the total number of bits you need, that's your input size. And it's usually going to be much larger than n, right? Because each number here may have, n to the 4 digits. So this is the size. The larger the number is, we need more time to solve the problem. That's a natural way to present a function. Let's say here the input is a matrix and somehow this function, well, here you just have to specify p for the p norm and so on. And quadratic form, you have a matrix defining this and so on. But sometimes you want to deal with more abstract functions, like if the function is convex and concave, and it may not come with a formula. So how do we present a general function and just use in the algorithm that this is convex somehow? So then we are going to use oracles. So in Oracle, there are two natural oracles. Let me write them here. So the first thing, what's the most natural oracle? So an oracle is a black box, okay? So I have access to the function and other objects later. For an oracle, this means I can ask questions about the function or the set later. And this black box gives me the answer. And the idea is that if I can design an algorithm in this setup, it is more useful, it's more powerful. Because then, if you have a specific implementation or application, you have to actually come up, you have to write a separate subroutine that materializes this oracle, that evaluates the function or whatever. So it's harder to design algorithms in the oracle setup, but they are more useful. And most of what I'm going to do here will work in an oracle setup. So what's the most natural oracle for a function? Evaluation. Exactly, you give it a vector and you get back the answer. Evaluation oracle. So that's the most natural oracle, evaluation oracle. So you ask or query, that's a common way of saying this, query x in Rn or in Zn and get back f of x. That's an evaluation oracle. And this means you have really little access to the function. You cannot see the global behavior of the function. I mean, you may assume on the side it has a property. It has a convex function, so you may exploit this. But you have only access to local structure, so it's harder to use this. And then there's an issue of whether you get rational numbers and so on. But there's a weaker oracle that is called comparison oracle. Comparison oracle. And this is just you ask about, query or ask about 2 points, x, y, and get what's the answer is going to be now. What? Yeah, which is bigger? Because for optimization, actually, this is really what we need. Just which one is bigger. And then you really don't know much about the functions. You just get the answer whether fx is less than or equal to fy or not. And if you ask about xy and yx, you can determine exactly the order relation between these. So, and most of our algorithms will be enough to use this. Okay, so let me move to the set now. So the set. So this is the function. Now let's talk about the presentation of the set. The set of points. And this is a more complicated issue, more important issue. So here there are two branches of the theory, and we are mostly going to concentrate on one of them. But in this introductory lecture, this first hour is just an introduction to give you some flavor of what is going to be. And starting the later lecture, we'll start developing some theory. So there are two branches of the theory here. And one is called combinatorial optimization. I mean, the partition here is not, the division is not strict. There are some intersection and there are some other things, but basically there are two lines here. Combinatorial optimization. So here, S is usually a set of 0, 1 vectors encoding some combinatorial structure which we want to optimize over. Structure. And the presentation of the set, okay, the presentation, well, how many vectors potentially you have? 2 to the n, right? You don't want to go over each of these points because this is exponential. We want to be more clever. And so even the presentation, you cannot give it as a list. So the presentation is either a compact, so I'll give an example, presented either compactly for some compact structure, and typically say a graph. I'll give an example soon. A graph is a typical example. Or by an oracle. Again, there are oracles or by oracle. By oracle, there are many oracles. Say membership oracle. What's a membership oracle? Yeah, you just give it a 0, 1 vector and it tells you, yes, it's in S, no, it's not. That's a very weak oracle. You have really little information. It's very hard to design algorithms, but it turns out that we can solve linear and nonlinear optimization problem with a membership oracle also. We're not going to discuss this here so much. So I'll just give an example. Let me just give, okay, so this is 1. 2 is what we call integer programming. I'll give an example and then we'll not talk much about it, maybe later in the end. Integer programming. So what is integer programming? It again has to do with the presentation of the set, and here the set S is a set of all integer points which satisfy a system of inequalities. So typically A is an m by n integer matrix, and B is an m-dimensional integer vector. And this is called integer programming. Now, of course, I have to tell you that we're talking about nonlinear discrete optimization. Is there a stick here somewhere? Well, figure out later. So we're talking about nonlinear discrete optimization, but even linear function, linear optimization is hard. Most of the literature actually in combinatorial optimization and integer programming, and this is where I take the names from actually, deal with linear objective functions. Because the problems are very hard already for linear objectives. They are NP hard quite easily, you can see. So, so these are integer programming combinatorial optimization. Now here, the inequalities are linear. Right? These are linear inequalities. But of course, you can talk about more general things yet. I mean, you can think about A instead of a matrix as a function, as m functions, and the function can be polynomials, for example. And this is what you've seen last week. So last week we talked about sets defined by polynomials. Let's call them A1. A1 of x less than or equal to B1, and so on. So this can be arbitrary functions, arbitrary polynomials, but we want also the points to be integer. So these are very hard problems. And so here we are not going to talk about this. We are going to talk about linear, where are the erasers here? Linear inequalities, but nonlinear objective functions. Okay, this is integer programming. And let me just give one, go and talk more in more detail on this. Let me just give one example of combinatorial optimization problem. So, and again, it's not going to discuss this much in the course. So here is a combinatorial optimization example. Spanning trees in a graph. So here's a graph. Let me use the example as in my notes here, actually. So, yes, so this is the draft of the entire book, which is going to be out. But what I have on the web, which is linked, is pretty good also. So here's a graph. Let's say the complete graph on 4 vertices. This is denoted usually by K4. Complete graph on 4 vertices. And we have some order of the elements. So these are the edges. Let's give them some order. So E1, E2, E3, E4, E5, E6. And then subsets of edges now are identified with 0, 1 vectors in dimension n. So a typical tree, let's say, so a tree, let's say a typical tree is, let's say, this one. E1, E4, E6 is a tree. E6 is a tree, right? You see this? Tree means a subset of the edges which has no cycle and spans all vertices. So it's connected, connects all vertices, and this is a spanning tree. So E1, E4, E6 is a tree, is a spanning tree. And if I want to write it now as a vector, then it's going to be a vector of length 6, 0, 1. So how does it look like? Can you tell me? 1, 0, 0, 1, 0, 1. And S is going to be defined here, the set of all spanning trees. So set of all span trees. And it's contained in 0, 1 to the n. Here it's 6. Okay, generally it's n is the number of edges, not the number of vertices, the number of edges. Okay, so this is the set. Now let's look on an optimization problem. So suppose we have a linear objective function first. It's Wx, where W is a vector like this. 3, 1, 2, 0, minus 1, minus 2. I hope I got it right. And let me also write this on the edges, the weights here. So now the coordinates correspond to the edges. So 3, 1, 2, 0, minus 1, minus 2. Is this clear? Now I want the tree which maximizes. So the problem now, this is a discrete optimization problem, is max Wx, so that x is a spanning tree. And you see, this is a compact presentation. The size of this tree is something like n squared, of the graph. The size of the graph is something like n squared, polynomial. How many trees are there? Well, actually, for the complete graph, there's a formula, like Cayley's formula. I'm not going to do this, but it's exponential. You cannot check all trees. So how do you find the best tree? Do you know? This is something very simple. Greedy algorithm. So here, this is an example of a very trivial algorithm. You just greedily pick the best. So 3 is the maximum value, right? You pick this one. What's the next best? 2, right? 2. What's the next best? 1. You see, but 1, if I put 1, I close a cycle. So the greedy algorithm tells you pick the next one, which does not close the cycle, and here it's going to be 0, and this is the best tree. That's very easy. But now we want to do non-linear. I see, this goes behind this blackboard, so you will not see it. It's not so good. We are in a problem. Okay, well, I have to use this one then. I think there should be a complete permutation. You can see, I see, then you have to go all the way up to 3, I3, there's only 2 here. That's, well, okay, so I want, okay, luckily we can do it here maybe. So now I want to look on a more general problem, non-linear, and it's going to be this. F of Wx, I'm going to show you one of this form here. And so I'm going to have 2 rows now. W is going to be now a matrix. The first row is as before, but now I put a second row. So each edge gets another weight here. So now it's -2, -2, 0, -1, 1, 2, 3. This is my weight. And then my function is going to be f is defined on 2 things now, right? So f of y equals f of y1, y2. I'm going to let it be y norm square. So this means that f of x now is f of x is the first row square as the second row square. This is the objective function, and you have the similar numbers come here. Each edge now gets 2 numbers, 2, 0, and so on. Right? Okay, let me do this. So now there's no greedy algorithm, there's no order on the edges anymore, because each edge has 2 numbers, right? So how do we find this? Well, can you do it in polynomial time? This is a harder problem. Well, it turns out you can. The answer actually here, the tree is different. You can check this. I mean, I'm running out of my time for this talk. So the optimal tree now is not this one, but it's this one. That's the best tree now. It's a different tree. You can check this. And it turns out we can actually solve such problems in polynomial time. For every fixed d, d is the number of criteria. And maybe in the end, the last lecture, I might be able to say something about this, because this is a little bit outside of what I want to talk about. So this is combinatorial optimization. Going back to integer programming, this is the main topic. So integer programming. Let's see, is there any, no, there's no way, huh? 2 and 3 means always 1, there's a risk of 1 being behind. Okay, so integer programming. So S now is a set of integer points satisfying a system of linear inequalities. Here's one example, immediate example. I get numbers A0, A1, AN in Z plus. This means positive integers, no negative integers, let's say. These are no negative integers. So here is an example. S equals x n such that sigma AI this is a simple example of an integer program. The data are these numbers for this problem. This is a natural encoding of the, yeah? What? Yeah, thanks. AI, XI, good. Yeah, thanks. Of course. So integer vectors, the definition, I mean, the set is defined in terms of these numbers, the binary representation of these numbers. You have a single equation. Equation, of course, a special case of a linear inequality. Just take less than or equal and greater or equal. So a single equation, the inequalities, the bounds and the variables are also inequalities. This is an integer program, very simple. Can you solve it? Can you just check? I mean, a special case of optimization is deciding if a problem is feasible, if it has any solution, right? Because if you minimize, then if the set is empty, your objective function is plus infinity. So feasibility is a special case of optimization. And can you decide if such a set is empty or not? So people that know some complexity recognize this problem. This is a so-called subset sum problem, and it's a classical NP-complete problem. Subset sum, NP-complete, so this is very difficult. It's probably not going to exist a polynomial time algorithm. So you see these problems are very difficult, even if we have one equation. You immediately get into NP-complete situations. So what can we do? I mean, this seems a little bit hopeless. It's such a simple problem, one equation. Well, there are various things we can do, and we will show you that we can do, but the first thing you want to think about is something that actually you've seen last week. Well, last week they didn't talk about polynomial time so much, but if you remember, there was various relaxations, degree-bounded relaxations. There was some parameterization so that for each fixed parameter you can solve something, do something better. So what's the most natural parameterization for an integer program, not this one, I mean in general here? What's the most natural parameterization? Yeah, that's a good point. I'll come to this point later, but that's not a parameterization. That's relaxation. We'll say something about this. So relaxation is important. Well, not so much for what we are going to do here, but I'll say something. There's one parameter which sticks out clearly, it shouts, I mean. N. So the dimension, right? So you can parameterize the dimension. So for each dimension is one parameterization. Dimension means the number of variables. So for each fixed dimension, there exists a polynomial time algorithm. And if I fix n, so why isn't the problem fixed? Oh man. Because still the numbers here, a and b, may have large numbers. This is the input. So fixed dimension, we fix the dimension, there is a polynomial time algorithm. In application, it's a little bit restricted because the number of variables is fixed. But it is very useful still, and it comes up as subroutines in many situations. And this is exactly where the lectures of my lectures and Matthias's lecture are going to split. And so Matthias is going to develop the theory of fixed dimension. So Matthias, the talks of Matthias, theory of fixed dimension. And I'm going to talk about variable dimension. So my lectures and my monograph deal entirely with variable dimension. And we'll see that we can still solve many problems of polynomial time. And in particular, we're going to get a different parameterization. And I hope I'll have some chance to say this, to explain this later. So this is Matthias and my talks, my lectures. Variable dimension. But on the way, I mean, I'm going to solve polynomial time problems here, but on the way, and I hope I'll have time to explain this, there's a whole chapter in my book on this. On the way, we give a different new parameterization of all integer programs. So different new universal, so this is a universality phenomena. So this means, again, there's going to be one parameter so that every integer program falls into one of these classes with this fixed parameter. But whenever you fix the parameter now, the programs that come in this class are not fixed dimension. They have many programs in variable dimension, and you can solve them efficiently. So let me give some examples analog to this for integer programming. Okay, so integer programming examples, IP examples. So first of all, let me talk about permutation matrices. So here is one. Permutation matrices, or so-called assignment problem. The assignment problem. So what are permutation matrices? You know what they are, right? N by n 0, 1 permutation n by n matrices, so that in every row and every column you have 1, 1. How can I define it, write it as an integer program? So the set S of all permutation matrices is a set of all Zn, let's see. Integer program, let's say m by m, because I want to keep. So n is really going to be m squared here. M by m permutation matrices, such that first of all they have to be non-negative, and the sum on each row and column should be 1. Sigma I xij equals sigma j xij equals 1 for all I and j, and x is a non-negative matrix. Or let's say each entry is non-negative. So these are precise permutation matrices, right? And the optimization problem, let's say the linear optimization problem, max Wx such that x and s permutation this is the assignment problem. So here I just mean the inner product in the matrix space. Just think about this as vectors. Okay, not the matrix product, just as vectors, long vectors. W is now a matrix. That's our linear function. M by m. And the interpretation is that Wij is the value of assigning worker j to job I. That's the assignment problem. I was hoping I will not need to erase this blackboard because the erasers are really bad here. So, well, technical problems. So let me continue here. Some cleaning. You actually have to. Not so bad. So in Zurich, they have a very nice machine. A cloth, something like a stick with a sponge. You can wipe it wetly, and then immediately there's a rubber that takes it off. Fantastic. You do it, and then the blackboard is clean. So. Okay, so do you understand the interpretation there? You have n jobs, n workers, n jobs. You want a perfect assignment of jobs to workers. And suppose that you look in the CV and the qualification, Wij represents the value of assigning job j to worker j to job I. And you want to find this permutation, this assignment which is the best. So this is really a nice interpretation. By the way, can you solve this in polynomial time? What? You're nodding, yes? So how can you solve it? Max flow. Yeah, so there are algorithms for this. There are simple combinatorial algorithms. Flow, if you study some graph theory course or something, you can solve it combinatorial using flow techniques or using linear programming. And, well, I prefer the linear programming. I'll tell you soon why. But so you can solve this in polynomial time. But it's not as simple as the greedy algorithm for the spanning tree. It's more sophisticated. Yeah. So this means just Wx means sigma ij. Standard inner product. Okay? So it's a number. So the algorithm is more sophisticated than greedy algorithm, let's say linear programming or flow algorithms, but you can solve it. Let's look at a more general problem than this, transportation problem. So now the story is the following. You have these suppliers, and they have supplies. So this one wants to supply S1 units, S2 units, and so on up to Sm. There are consumers. They have consumptions 1, consumption 2, consumption n. And there's a whole graph, complete bipartite graph here. You know, every guy is connected to every other guy, and so on. This graph, by the way, is denoted by KMN, the complete bipartite graph on M and N vertices. These are integers numbers, so the Si and Cj are integer numbers, non-negative integer numbers. And there are capacities on the edges on each. So this may be thought about as oriented, but you have a Uij, which is a so-called capacity, upper bound. So demands, supplies, Si, consumptions, Cj, capacities or upper bounds on the capacities, Uij on edges. And then there's, let's say, a linear object, or let's say it's an, okay, let's say linear and linear objective, linear cost, Cij, again in Z plus, or that doesn't have to be plus, for unit flow on I to j. This is the problem. So is the problem clear? We want to find the minimum cost flow or transportation. The problem is to find min cost transportation. So is this clear? What I want to find to assign the transportation mix min xij in Z plus. So I have to tell you how much flow, how much supply, integer supply, non-negative integer, to send from each supplier to each consumer, so that the total number of flow on each edge does not exceed the capacities, and the total cost is minimum, and each supplier sends exactly all his supplies, and each consumer gets all his consumptions. So this is an integer programming problem. Again, now you want to minimize Cx, sigma Cij, Xij, such that, very similar to the assignment problem, the sum of the suppliers, that's the consumption, Si, and what else? Xij less than or equal to Uij, and Xij non-negative and integer. This is the transportation problem, the classical transportation problem. It's an integer problem. So can you solve it in polynomial time? I'm running a little bit short here with time, not polynomial time. Exponential time here. So can you solve this in polynomial time? Well, the same thing as before, either by flow or by linear programming. And let me so quickly say something about your question before, relaxation. So let me say something which is important, but we are not really going to use it in these talks so much. Well, so let's look on this set over there. So S, let me write S for this set of flows, of transportations. Z n by n plus such that sigma xij equals Cj. There's a set of integer points, right? So it is obviously contained in the convex hull of S. Now let me, I want to say this later. It's contained in the same set where I put reals here, and the same constraints here. And this is the so-called continuous relaxation. So this is contained in this. The same constraints, only here I require the points to be integer, and here I allow them to be real, non-negative. Non-negative real. So this is contained in this. This is a larger set. And, well, it turns out that if I take the convex hull of this now, okay, let me do this. What about the convex hull of this? Is this still contained or not? Well, the picture is the following. This S is not going to be a nice picture because, I mean, it's a little bit, let's say, a d-dimensional picture. Let me try to do something. Suppose this is my set S. Now the convex hull is this, right? This one is a convex set by definition. Set of points defined by linear inequalities is a convex set. So this one is usually something like this, maybe bigger. This is the relaxation, and this is the convex hull of S. Okay? But for the transportation problem, we have equality. So this is just for the transportation problem. We have equality, and this implies we can use linear programming, continuous linear programming. So I'm not, again, if you've not seen this, this may be a little bit not so clear. It's something to think about, and I hope in the recitation later this afternoon, maybe you can say something about totally unimodular matrices. So this is a very specific situation for the transportation problem, and this explains why I can do it in polynomial time. There are also combinatorial algorithms, flow algorithms, but this is really what's going on behind, why this problem is easy. Because you have equality here. So the picture here is actually they are the same. And linear programming now, so now we have a continuous problem. You use linear programming solver, and you will get an optimal vertex, and that's going to be an integer point, it's going to be a feasible point. So that's an easy situation. And let me just say why. The reason, if you write this in a matrix form, so how are we with the blackboards here? Let me move down here now. So the reason for the equality is because if you write, I mean the same S there, if you write it in our standard form using a matrix, then this matrix A, which defines the system, is so-called totally unimodular. Then A is totally unimodular. That's something we're not going to talk about. So in this course, we are not going to talk about this much. This is the easy case. We're going to talk about things which are harder. But let's just say that the matrix looks something like this. This is how if you write this down in a matrix form, the matrix will look like this. So it has this nice two-block structure with ones and zeros. The matrix has a property called total linear modular, and this guarantees that you have equality there and you can use linear programming. This is the easy case. So let me move to a harder case. This is easy. This is our actually starting point. But we want to do better, deal with harder problems. And this is going to be my last example for this hour. So there are various extensions to tables, actually. So there are extensions, multi-way tables, so multi-indices, xi, jk, and so on. That's one very useful extension that comes up in some statistical applications. We are going to talk about this later. Actually, this is chapter 5 of the monograph. But I want to talk about multi-commodity transportation. Because then it is easy to set up the same program there. So what is a multi-commodity transportation? Or actually, you can talk about arbitrary directed graph, then it's called transshipment. And again, our time is limited. Also transshipment, that's for any graph. So that's any graph. But let's look on transportation. So what is the multi-commodity transportation? Well, instead of one type of commodity and flow, there are several types. So each consumer and supplier now have supplies and consumptions in L different commodities, which should be matched separately. So we now have also each supply is an upper a superscript where K goes from 1 to L, and these are different commodities. So that's a more complicated problem. So each supplier has L positive integer numbers, which tell you what is the supply that he wants to supply in each of the commodities. And the same for the consumers. Is this clear? The objective function, let's talk about the objective function in a second. But how about the capacities now? So let's look on the constraints of this. Constraints defining the set. Right, so we have M suppliers, and consumers as before, and now also L types of commodities. Commodities or goods, I don't know if this is a common term. Okay, so first of all, we still have, like before, we want the xi, we have xi jk now. This is going to be the flow of commodity K from supplier I to consumer J. So actually you see, our variables now are triply indexed, and this is, for you may have indices this way or more indices. There are various problems here. And we have, again, consumption and Let's say I sum over the consumer over the suppliers, so what should this equal? If I sum the total flow of commodity K over all suppliers, then what should this be? Total consumption of J, this is the free index K. So consumer J should get of commodity K this much flow. And similarly, there are these other sigma J xijk equals Sik. Now, again, xijk should be non-negative integer, and there should be something about the capacities. So what about the capacities? All right, so the question is, should you have a separate capacity for each commodity or one joint to all commodities? One joint, because otherwise, it's again the previous problem. It just splits up, breaks up, and becomes separable to, right? So that's the point. So what makes the problem harder now is that you have to sum over all commodities on the same edge, and this should be less than uij. I should say that this problem is quite applicable. I mean, again, you know, we're doing theory, but this is really close to, and you can think about either traffic networks, railroad. I mean, there are lots of work on scheduling trains, railroad transportation. But you can also think about the internet or, you know, communication, computer communication networks, cellular phones, and so on. Again, you have capacities, edges, and so on. You want to find the minimum cost transportation. And so what do you think about the complexity of this problem? This, I said, we have total unimodularity. We have equality of the convex hull and the relaxation here. Very nice. You can use linear programming or flows. How about this problem? Suppose I have two commodities. L equals 2. So where can we use this blackboard? Use this one. How about the complexity of this transportation problem with two commodities? So, complexity of the, say, L equals 2 commodity transportation problem. Well, we learned something, right? We can look on the relaxation. So let's try this. So what can we, suppose we just want to think about this. Convex of all, well, x such that xijk and all these constraints. Supply, consumption, what else? Capacity, constraints. This is my set. And let's say these are, I want these to be non-negative integer. Let's look on this. So, well, I need maybe 5 minutes more, so let me slow a little bit. So do you understand what have I written there? Without a convex hull, if you just look on the set, this is the set of feasible two-commodity integer transportation, right? I have a variable for each supplier, consumer, and commodity. I assume now two commodities only. So the first extension of the usual transportation problem. I have the supply and consumption constraints these. I have the capacity constraints these, and that's the problem. And now, as I said, let's try this. So we take the convex hull. We know it's contained in the set of the same set. Then I have real non-negative things. So how can we check? I mean, are these equal in general? Or? Well, it's kind of obvious, right? Otherwise, I would not bother to. So there's an inequality here. Let me give you an example, which is in the notes. So here, and this is immediately implies. I mean, if if you fill this area, once you have this situation, it almost immediately implies this is NP-hard in general. But we will be able to solve this. So let me just. I want to give you just a quick example where actually you have inequality, very small example, and then I want to tell you what the optimization problem here is. So let me draw one example where we have inequality. Yeah, what is this? So here's an example. Let me give you the example. I think it's quite interesting to see. So we have n equals 6 suppliers, n equals 4 consumers, n equals 2 commodities, and the capacities. So the capacity matrix U, I write it as a matrix. I have a capacity for each edge, for each pair supplier consumer. It's very simple: 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, like this. That's the capacities. Let me tell you what are the supplies. Supply, let me write down. So the first commodity, let me write down as a vector. So these are the supplies in the first commodity for each one of the 6 suppliers. So this is 1, 1, 1, 1, 1, 0, 0. S2 is the vector of all supplies of the 6 suppliers in the second commodity. So 0, 0, 1, 1, 1, 1. Then we have the consumptions. So consumption in commodity 1 of the 4 consumers is actually the same as consumption 2 of the 4 consumers. This is 1, 1, 1, 1. And if you look on this data, there's a single solution. There is a single real solution flow, a transportation, okay, let's flow, but no integer solution. And the solution will, let me write this. Oh. Let me write it small, like this. So x1 is the flow of the first commodity from each supplier to consume. It's half times this. And this example is not so easy to come up with. I mean, it's not a coincidental example. We'll say something about how can we find such examples in a systematic way. Yeah. Let me finish with one last thing, and then I'll go to break. So is this example clear? You take this problem, write it down, write this. The top set, the convex hull of the integer point, what is it? The top set. The empty set, there's no integer solution. This is the only point. And the bottom set, the relaxation is exactly 1 point. This one, the fractional one. So this is an NPR problem. But we will be able to solve it in some situations. And in particular, we will develop a theory that allows to solve such problems, multi-commodity problems, in polynomial time, of course under some assumptions. We are not showing that P equals NP here, under some assumptions. Even with nonlinear convex costs. And let me tell you what do I mean by that. So what is the cost of a flow of the form sum over all edges? What is the standard linear cost of a commodity transportation? So the standard thing is something like this. So I need 2 more minutes, and then I think this is important. This is the standard linear objective which we want to minimize. So you see what is written here. What is this here? You see this here? The same expression is here. What does this mean? I sum over all commodities xij_k. It's the total flow from I to j on one edge. That's the total flow on all commodities combined. That's the total flow from I to j. And we want this to be less than the capacity, but we also, suppose we have a cost, Cij, cost per unit flow on this edge. Let's think about computer network. I don't know, maybe this is costly. It goes from the US to Europe. So the linear problem, you just multiply this number by this. But now, think about traffic, for example. So suppose you, I don't know, go from here to San Francisco. If you go in the rush hour, what happens? Much slower, right? If you have lots of traffic, or if you access MSRI, if you access the site of this workshop now, you know, you want to hear me. So I hope there's lots of traffic. But anyway, if you have lots of traffic, then it's not linear anymore, right? There's congestion. And the objective is actually something which may look, a more realistic objective is something like this, maybe, where Fij may be some convex, something like this. So this is this is the flow. This is Fij. So maybe Fij of y, ij, let's call this yij. Maybe it's yij to some power, I don't know, to 1 plus to 3/2. Makes sense, right? The more traffic you have, you pay more. And so this is a nonlinear objective. It's still even harder than this NP-hard problem. But under some assumption, we will be able to solve this in polynomial time. So let's stop here. Okay, thanks. We have a coffee break. And after that, Matthias will